Hi everybody, just another quick problem for Chapter 10. This is from Chapter 10, Section 5, where we're testing the um, question of whether or not the variances of two populations are the same or not. In this case, we're given two samples, one of 9 items drawn from some population, we don't know what, that had a variance of 100. That means, of course, its standard deviation was 10, but we're really interested in variances right now. And the question is, if we take another population and draw a sample of 7 items from it and get a standard deviation of 20, can we assume that those two populations have different variances? Now, it looks to me like 20 versus 100, sure, there's a difference in variances. But is it really statistically valid? And that's, of course, what we do every week in this class. Now, the two hypotheses we're looking at here. First of all, the null hypothesis is that the two variances are the same, and the alternative hypothesis is that they're different. Okay, what could be simpler than that? And of course, we always need an alpha value, so we're going to use 0.05. And of course, you note that this is a two-sided distribution. Sigma 1 could be greater than sigma 2, or it could be less than sigma 2. And when we see a not equal to sign in one of these hypothesis tests, we have to, of course, divide alpha into two pieces, one for the left tail and one for the right tail. So we'll immediately take alpha down to 0.05 in a minute. Now, the only this testing business is really pretty simple. The only thing we really have to do is calculate the ratio of sigma 1 to sigma 2. Now, the way the F tables are set up, we always have to make sure that we have the bigger number on the top and the smaller number on the bottom. That gives us a ratio that's going to be greater than 1. So in this case, I've done this ahead of time. Move it up one. We're going to have the ratio of sigma 1, which is 100, divided by the sigma 2, which is 20, which gives us a ratio of 5. And that's our F statistic. Now, the question is that bigger or less than the critical value? Well, as we know now, having read section 10.5, we have to use the F table at the back of the book, and we select one of the tables based on the alpha value. Now, again, I said that a moment ago that we're going to divide alpha into two pieces because this is a not equal to problem. So alpha is now 0.025. That's the table we want. We could go to the back of the book, but I've made a little section of that table here I'll bring in for you. How do you do it? I use the F inverse Excel function, which allows me to calculate a value of F for any numerator degrees of freedom and denominator degrees of freedom. You know, I just realized I did this problem wrong when I did it earlier. The degrees of freedom that we use in here is really the n1 minus 1, isn't it? So I've got this red thing here. We're in the wrong spot. John, how could you have done such a thing? Let's see if I can do it now. I've got the numerator degrees of freedom would be 9 minus 1, which is 8. And the denominator degrees of freedom is 7 minus 1 is 6. Oh, well, that's easy to fix because I use Excel. I'll do 6, 7. I'll do it 5, 6, 7. And now I have a new table and new values. We said 8 and 7 minus 1 is 6. So there's our value right there. So what does that tell us? I'll make it even red. This makes it nice. There's the value we're after. Now, 5.6 is greater than 5. That says that we have to accept the null hypothesis, that the two are equal. Isn't that interesting? Let's see. Yeah, that's right, isn't it? We can reject H0 only if our test statistic is greater than the table value, and it's less. So what that's telling us is that in calculating variances, to find out, when running a hypothesis test to determine if the two variances are the same, we set a pretty high standard, especially when we have small values of n and for the two samples. Let's say just for fun that we went to 100, sample of 100 for each case. That would give us 99 degrees of freedom here and 99 degrees of freedom here. Now our F value is down to 1.49. So, even a value of, I don't know, 20 and 20 would allow us to agree that those two variances are equivalent, or are equal rather. But because we have such low values of n, such small sample sizes, we can't make that conclusion. We don't have enough information. Okay, that's how you do these problems. Incidentally, if it had been a greater than or less than problem, we simply would have not divided alpha into two pieces. We'd use the 0.05 table. And again, we'd make sure we'd had the big number on top and the little number on the bottom, and then we would away we go. So we'd have a F statistic now of 4.15, and we could accept the null hypothesis that instead of being not equal to, let's see, it would be, we've got S1, S1 would be greater than, make sure I'm saying that right, I got to think a minute. You always have to think about these things, don't you? Yeah, if it's, the alternative hypothesis would be greater. Yeah, sigma 1 would be greater than sigma 2, of course. So, yes, we can say that sigma 1 is greater than sigma 2 because we now have a stronger value of alpha, a larger value of alpha. Okay, hope that helps. Good luck, and we'll see you online.